Hello everyone, my name is Kanglin, and I'm from Polytechnic Montreal, Canada. Today I will present our research work, Low-Cost Precision Monitoring System or Machine Tools for Small and Medium Enterprise. I will present our work from the following 5 areas: background, machine tool errors in CNC controller, low-cost precision monitoring system, its orientation of the Achiche system, the results and the conclusions. In order to improve the machining quality and efficiency, condition monitoring system is being widely researched and applied in industry. Generally, the monitoring objective can be classified as 3 main areas. One is the machine tool components, machining process, and the machine tool accuracy states. Whereas for the application of digital manufacturing solution, especially for the condition monitoring system, in small and medium enterprise, they face the following questions. For example, the nature of the technology assimilation, and then the fear of the high cost and the failure, then the diversity of the data form and communication standards, and the difficulty for the application of the digital manufacturing solutions. For example, the common data communication tool are the Internet, MT Connect module, Cyber OPC, and forecast. Well, in this research, we try to introduce a vision-based low-cost precision monitoring system. The precision of machine tools is defined by its positioning, accuracy, and repeatability. Take a simplified machine tool as an example. It has a tool and workpiece and also the kinematic chair. Owing to the non-existence of the machine tool errors, so the tool and workpiece can be fully meshed. However, owing to the existence of the geometric error, then the geometric error generates the orientation and the positioning errors of the tool relative to the workpiece. So there is a volumetric error vector. Whereas for the real machine tools, the direct error measurement methods including the laser interferometer, Barber test, R test, and also the laser tracer. Whereas for the machine tool errors in the CNC controllers, we can know that for the general CNC machine tools, they all have the error compensation table, and the table value are usually equal to the calibration results which are measured from the direct measurement method. However, we can know that for the monitoring purpose, we can read the data from after the calibration, or we can read the data just from the CNC calibration tables, rather than manually input or referencing the key threshold result. Whereas for the machine tools, it can be classified as 3-axis machine tools and 5-axis machine tools. For the 3-axis machine tools, the general error compensation tables are pitch error compensation, 3-tensor compensation, and the backlash compensation, and also other errors. Whereas for the 5-axis machine tools, apart from the mentioned errors, we can also compensate the volumetric error or the kinematic errors. Let's take the Fanuc 15i NC controller as an example. This figure shows the pitch error compensation table and also the backlash error compensation table. Well, as for the proposed low-cost precision monitoring system, it's easy to install low-cost vision-based monitoring system. It uses open-source software and low-cost hardware systems. The advantage of the proposed ETI system is it has good reporting and simple installation, and they can simply integrate it into the current resources of the small and medium enterprise without very high investment. In addition, it can be implemented without Azure technology support. Here, this is the architecture of the proposed ETI monitoring system for machine tools. And we can find that for machine tools, we can install the ETI system, and then those data will be processed by the compensation platforms in SCI or the Node-RED. And this process is realized in the cloud platform. And finally, the technician and the operator can access the processing results in the means of laptop, tablets, or phone. Well, as for the detail of selected software or hardware, we can find that we use the SCI lab and the Node.js software, which are open source, so they are very cheap. And this is a dashboard we developed for our ETL system. It mainly includes the main figures and also some subtitles such as piece error compensation, 3 error compensation, backlash error compensation, and other error compensation. Whereas for the hardware systems, we can find that we have a camera and also its development board, and also there is a human-made camera fixture, which using the gooseneck to adjust the position of the camera. To improve the signal range, we also use a chip link retainer. And finally, the calculation platform is in the ThinkPad and also the phone electronic platform. Whereas for the data processing steps, we can find that we generally using the 6 steps for the image data processing. Firstly, we need to capture the error compensation table, and then we will transfer the captured image to our local server, where it can do the the number representation. And after that, the recognized number will be translated to the error curves. And those results will be shown in the Node.js platform. And in addition, we also develop some algorithm which can detect the abnormal change and help the user to make the decision. Where we all know that different CNC controller and machine error parameters have different error compensation setups. So we use the following method to do the error translation. Firstly, based on our known CNC controller, we developed an error translator which can translate the recognized number to the error curves. Whereas for the new CNC controller or new machine tools, firstly we will compare the setup parameters of the error compensation table with a known one. If they are the same, we can use or developed error translator to do the error curve calculation. If not, we need to develop or modify the existing one to a new error translator, and then we can calculate our expected error curve. Whereas for the implementation of the ETL system, the demo is tested in our H4TT 5-axis machine tools in Virtual Manufacturing Research Laboratory. From this figure, we can find that here is a local server which is running in a single computer, and then this is our proposed ETL system. It will be connected to the CNC controller by magnet devices, and then it has a camera and some wireless data transformation module. We manually adjust the camera, which is normal to the CNC controller screen. And then, after 2 seconds for the data acquisition, the data will be transferred to the local server for the deeper data processing. For experimental machine tool, it has a FANUC 15i NC system. It has many error compensation tables, but in this research, we just focus on the pitch error and backlash error compensation tables. And here, this is the pitch error compensation table recognition results. And from this figure, we can find that this is the original conversion result of the XSS listener position error. And after the initial data processing, we can calculate the error compensation values for our machine tools. And those errors has been improved in inputs to the CNC controller. And then we use our proposed ETL system to recognize the number. And then the results will be shown to the Node.js system. And also, we can read the result from the tablet and the iPhone. We test 50 pictures and we have a 95% recognition rate. However, we can't overlook that the recognition results can be affected by lighting. the capture angle, and the camera's maximum resolution. You see here, this is a recognized axis linear position curve. And this curve is matched with the original error compensation table. And this is a backlash error compensation table recognition result. And from here, we can find that this is the original error compensation table results. And those results are the recognized results using or proposed ETI systems. And compare with the recognized result and the original result, we can find that the two results are precisely matched. So our proposed systems are effective. So the proposed ETI system is suitable for recognition machine-to errors, such as pitch error and backlash error. Next step is to develop and validate with other error parameters. Although it works well, it also has the following some limitations. Firstly, the recognized machine error parameters cannot be the exact collision result, and it can't reflect the real-time machine-to-precision state owing to the jet lag of the real machine tools and the error compensation table. Well, some human intervention is still needed because the camera needs to be manually adjusted. And then the recognition result can be affected by the camera's lighting and installation. So next step, we also will be develop some solutions for those problems. Okay, this is my presentation. Welcome for your comment and suggestion. Thank you.